Let's consider an implementation of nonlinear programming models for the inventory management problem. Here we consider the simplest supply chain in which there is a supplier which supplies a retail shop. Assume that this is a retail shop, and the shop supplies its customers. And so the problem is the following. Assume that our customers continuously consume our product. For instance, we assume that our product is orange juice. So assume that customers continuously buy our orange juice, and we make orders to our supplier, and we every time order a certain batch of orange juice, so a certain amount of liters of orange juice. And the problem is in our shop, the inventory management policy. So to understand, to describe the inventory management policy, we should consider two questions and find answers to these two questions. The first question is how much to order every time, and when to order. We should make decision about these two issues: how much to order and when to order. To answer these two questions, we will consider a certain model which is non-linear one. To start, let's consider the total average cost function. So, total average cost, it will be the performance criterion which measures the quality of our inventory management policy. And for this reason, to estimate how efficient our inventory management policy is, we will consider, for instance, total average cost function. We do not consider total cost function, because if we consider inventories, in most cases, inventories brings cost. So, for instance, if we consider orange juice, we invest our money in orange juice, but we could invest this money in some other goods or projects, and maybe we may get more money. But we invest our money in goods, in orange juice, and also we should maintain temperature, we should secure, and we should keep these inventories at warehouse, and we should pay rent cost and so on. So usually inventories bring cost. And for this reason, we consider the cost function. And if we assume that our company works for infinity, so total cost will be infinite. So, but to make sense, we consider total average cost. So it is the cost per time period. And let's consider the terms or parts of this total average cost. First of all, purchase cost. To sell something to our customers, we should buy something from our supplier, and for this reason we should pay purchase cost. So for instance, if we buy 100 liters of orange juice, we should pay a certain price for each of these liters, so we should pay purchase cost. And which cost also appears. Assume that there is a purchase manager in our shop, and for each order he makes, we pay him bonus. And this bonus does not depend how much he orders. So if he orders 1 liter, we pay him $1. If he orders 100 liters, we pay him $1. So this fixed cost to make an order does not depend on order quantity. Also, if we consider a bigger company and international deliveries, so this fixed cost could also include dispatching cost, so we should control delivery of our goods from another country, for instance, and it doesn't matter 1 container or 100 containers we deliver. So anyway, we should control this delivery, and we bring certain fixed cost or administrative cost for each order. So the first term, it is the purchase cost, and the second term, it is the fixed cost, which does not depend on order quantity, and purchase cost does depend on order quantity. The next one, holding cost. Assume that we bought 100 liters of orange juice and our supplier delivers these 100 liters of orange juice to our shop. We should keep this stock at our shop, and for this reason we should pay holding cost. And once again, it could be temperature maintaining, it could be secure, and some other cost. And the next cost which may appear, shortage cost. So for instance, if we have no orange juice at our shop, but our customers needs orange juice, so some shortage cost may appear. For instance, if a customer asks for orange juice, we say, sorry, we do not have orange juice right now. Are you ready to wait? And if our customer is ready to wait, but he may say, for instance, I would like to wait, but if you propose a discount for me. If we agree with this deal, so shortage cost, it is the amount of discount. The discount size, it's like a shortage cost. In our discipline, we will consider the simplest model of inventory management in which there is no shortage cost, because shortages are forbidden. And we will consider only these three terms: purchase cost, fixed cost to make an order, or administrative cost, and holding cost. So it is the term 1, it is the second term, and it is the term number 3. And let us repeat. Term number 1 does depend on order quantity. Term number 2 does not depend on order quantity. Term 3 does depend on order quantity, because the bigger our order, the bigger the batch we should keep at our warehouse or at our shop, so the bigger holding cost. Inventory management is rather rich discipline, and there are a lot of models which are used in different cases. I would like to consider the following classifications of inventory management models. So the first models, so the simplest one, is static deterministic inventory management models. So what does it mean, static deterministic? Deterministic means that demand, for instance, is predictable. We know that our customer every week consumes 100 liters of orange juice every time, forever. And it means that our problem is deterministic. And also, what does it mean, static? It means that our customers consume 100 liters per week, this week, next week, and so on. So no changes. So the problem is static. And the next case is dynamic deterministic inventory management models. Here, the demand is once again deterministic. We know for sure future demand, but we know that this demand changes over time. For instance, this week, according to our contracts with our customers need 100 liters of orange juice. Next week, they need 50 liters of orange juice. We know for sure these 50 liters, this demand for the next week. So demand is deterministic, but we see dynamics. This week is 100 liters, the next week 50 liters of orange juice, and so on. The next week, for instance, demand is 20 liters of orange juice. Once again, 20 liters is written in our contract, so we know for sure this demand. Demand is predictable, but demand is dynamic, because this week it is 100, next week is 50 liters, next week is 20 liters, and so on. We know these numbers, but we see there is a dynamic. In the first case, every week it was 100, 100, and so on. So deterministic the first case, deterministic the second case, but there is the certain dynamic in the second case. The next one, static stochastic inventory management models. In this case, we assume that, for instance, demand is stochastic variable. So, for instance, this week demand is 100. We do not know for sure what is the demand for the next week, and we wait for this next week and we see, demand is 102 liters of orange juice. We wait for the next week and the demand is assume that it is 98 liters of orange juice per week, and so on. We see that demand is stochastic, but for instance, mean value is 100 liters of orange juice. So mean value, mathematical expectation, and variance in demand remains the same over time. So there is uncertainty, but every time we calculate expected value of the demand, so mean demand, and mean demand remains the same. But if we consider dynamic stochastic inventory management models, in this case we see that demand can be a stochastic one. So for instance, 100 first week, 105 next week, 107 next week is 200s, next week is 300s, and so on. We see that mean demand increases, so it is not constant value. So even mean demand increases in this case. So, and this case we call dynamic stochastic inventory management models. So complexity increases from the top to down. So complexity, I mean complexity of mathematical models increases. But from another point of view, practical implications also increases from top to down. So dynamic stochastic inventory management models are closer to reality rather than the first one. But nevertheless, in our course in quantitative methods of decision making, we will consider only static deterministic inventory management model. So our goal now is just to consider the implementation of the nonlinear programming models for the real cases, and we consider for this reason the simplest case, static deterministic inventory management models. And this model is known as economic order quantity model, and the abbreviation is EOQ. Economic for E, order for O, and quantity for Q. Economic order quantity model, and the assumption is demand rate for resource is, for our orange juice, is constant, lead time is 0. We start with this assumption. Later we will relax this assumption, and we assume that there is no shortages in this case. And let's consider what does it mean demand rate. Demand rate, it is like a speed of consumption. So what is demand? Demand is, for instance, 100 liters of orange juice. But what does it mean demand rate? Demand rate means 100 liters of orange juice per week. So this is the demand rate, and this is the difference. So how much do we consume per time period? And let's consider our notations. X small, it is the order quantity, how much we order from our supplier. D capital, it is demand rate. So demand rate, for instance, 100 liters per week. T small, 0, it is the order interval. So what does it mean order interval? We will consider very soon. The next parameter, F capital, fixed cost to make an order. So it is the bonus which we pay to our purchase manager, for instance, for each order he makes. H small, it is holding cost, so it is marginal cost per time unit. For instance, if we pay for holding 1 liter of orange juice for 1 week at our shop, we pay H. if we keep 2 liters of orange juice per 1 week, so we should pay 2H. And also, if we keep 2 liters of orange juice per 2 weeks, so we should pay 4H. Z of x, it is the average total cost. So it is this function which we discussed before. So it is the total average cost. We now denote this like Z of x. And if we consider, for instance, demand rate for week, if we consider time period 1 week, so total average cost means that we consider total cost per week, per the same time period. The next, C small, this is the price for 1 liter of orange juice which we pay to our supplier. So this is the marginal cost. And X small star, so it is the optimal order size which minimizes total average cost. And we call this total order quantity economic order quantity. Once again, it is EOQ. We call economic order quantity model the model itself, which we consider right now, but also the optimal order quantity we also call economic order quantity, EOQ. Now let's consider the dynamics of our inventory at our shop. So let's consider the following graph. And the horizontal x is time and the vertical x is inventory. Assume that we order x liters of orange juice, and so we have x liters at our shop or at our warehouse, and our customers continuously consume our orange juice. And the moment before we run out of stock, we make a new order, lead time is 0, we immediately obtain, we receive this amount of orange juice. So, and once again, we continue with this amount. Assume that every time we order the same amount X, so we once again receive X liters of orange juice, and once again our customers continuously consume our orange juice, and a moment before we run out of stock we receive the new order, and the next dynamics is the same. These lines, this one and also this one, they are parallel because we assume that demand rate is constant in our case, so every time our customers consume the same amount of goods. So, and what does it mean, order interval? Order interval, it is the time period between two moments when we receive two successive orders from our supplier. So it is the dynamics of our inventory, and also assume that every time we order 10 liters of orange juice, assume that X equals 10. So maximum amount is 10, minimum amount is 0. So what is the average inventory? So we should calculate our average inventory. At each moment of time we have a different amount of orange juice, so 10, 9, 8 and so on. So to calculate the corresponding cost, so we should consider some average amount of inventory which we keep at our warehouse. Okay, maximum amount is 10, minimum amount is 0. So what is the average inventory? So average inventory is 10 over 2, it is 5 in this case. But if we consider order quantity X, so in general case, average inventory we may find like X over 2. So X over 2, it is the way how to calculate average inventory in our case. And also the same picture is available at our presentation. So the same picture, so and also average inventory is represented. Now let's consider how to calculate order interval. Assume that every time we order 20 liters of orange juice, and assume that demand rate is 10 liters per week. So we order 20 liters and the demand rate is 10 liters per week. So the question is, for how many weeks this stock 20 liters will be enough to satisfy demand? So the answer is 20 over 10, so it is 2 weeks. And the formula for order interval is x over d. So order interval is x over d. So in this case it is 2 weeks. So and order interval could be found as x over d. And also let's consider the following example. Assume that our customers need 100 liters per year. And assume that every time we order 20 liters of orange juice, our customers need 100 liters of orange juice per year. Every time we order 20 liters of orange juice, the question is, how many orders do we do per year? So the answer is 100 over 20, so it is 5 times we make order per year. 5 times or 5 orders per time period. So and formula is d over x. Now let's try to invent the formula for the total average cost function z of x. So z of x could be found as follows. The first term is the following. We should buy our goods, and we assume that demand rate is d units per time period. Okay, so for instance, per week our customers need d liters of orange juice. We pay for each liters of orange juice to our supplier C, so our purchase cost, term number 1, is C times D. The next term, fixed cost to make an order. So previously we discussed that how many orders do we do per time period. So the formula is d over x. So we make d over x orders per time period. And for each order we pay bonus to our purchase manager, which is F. So as a result, term number 2, fixed cost to make an order per time period, we may find like F times D over X. And the holding cost. Average inventory, we already discussed. We may calculate like X over 2. And holding cost per time period per 1 units of our stock is H. So, and as a result, this term number 3 is H times X over 2. And the formula for Z of X has the following form. C times D plus FD over X plus H times X over 2. If we go back to our presentation, the same formula we can see here at our slide. So, and also we assume that we order none less than 0. It is impossible to order negative amount of orange juice from our supplier. And our problem is to find such an order quantity X which minimizes this total average cost. So we need to minimize our total average cost function. So let's look at this example and let's consider what is the graph of such a function z. And to consider what is the graph of the total average cost function, let's consider numerical example. In this example, we assume that we consider different order quantities. So we can assume that the first option is every time we order 1 liter of orange juice. The next option, every time we order 2 liters of orange juice, and so on, till the order size 22. It's enough for our example. We assume that price for 1 liter of orange juice is 1. Every time for each liter of orange juice we pay $1 to our supplier. Fixed cost to make an order is $30, and demand rate is 2 liters of orange juice per week. And also we assume that holding cost is $6 per 1 liter of orange juice per week. So let's consider the total average cost function z, which consists of 3 terms, and the first term, it is c times d. So c is 1 times d, it is 2. So, and as we can see, term number 1, it is $2. And as we can see, c times d, so it is just a production of 2 parameters. No order quantity here. It doesn't matter how much we order every time, the first term is constant. Let's consider the second term, administrative cost. It is f times d over x. And now for the first case we consider x, order quantity, 1 liter of orange juice, and the second term, administrative cost, is $60. And if we consider this third term, so it is the holding cost, so we calculate this like h times order quantity over 2, and the holding cost is 3. So all of these volumes, term number 1, term number 2, term number 3, are given for 1 week. So, for instance, if demand rate is 2 liters of orange juice per week, and if we order every time 1 liters of orange juice, so it means that per week we should make 2 orders, because this is the demand rate, we should meet this demand. And for each order we pay $30, and if we make 2 orders per week, we should pay this $30 twice per week, and that's why the second term is $60 per week. And let's calculate Z, so total average cost for week. So we just summarize these volumes, and we get $65 per week. So it is the total average cost if we order every time 1 liter of orange juice. So let's continue, and let's calculate term number 2, term number 3, and Z for the next case. So when we order 2 liters of orange juice every time. So we see that the first term is the same, $2. The second term, administrative cost, goes down 2 times. So instead of $60, now we pay $30 per week. Good idea. So, and yes, holding cost rises a little bit, but our Z, total average cost function, now is $38 instead of $65. Good job. So I like these calculations. So, and now we may continue the same way, and we see that if we every time order 3 liters of orange juice, our total average cost is $31. So I see that there is our competitive advantage. So we may calculate our inventories, and changing this amount of order quantity, we may see, we may control our total average cost. So let's continue, and the next calculation is the following. So if we make an order 4 liters of orange juice every time, our total average cost is 29. Now let's continue these magic calculations, and if we order 5 liters of orange juice every time, we see that there is no difference in Z. Okay, unfortunately, but let's try again. And if we order 6 liters of orange juice every time, we see that our total average cost start to increase. And if we continue the same fashion, we see that our total average cost function increases. Yeah. So let's look at this graph and let's try to understand what does this graph mean. So the first term, C times D, $2, I do not show at our graph because it is just a horizontal line, and to simplify our visualization, I just do not show this horizontal line about $2 at this graph. So the next line is term number 2, and this is the fixed cost to make an order, administrative cost. We see that the higher volume of order quantity, the lower volume of administrative cost, and this is the blue line. And for this reason, let's consider the blue color for this column, for these numbers. So let's consider the term number 3. This is the holding cost. So the bigger order quantity, the bigger holding cost, because we should keep bigger amount of orange juice at our shop. So, and this is the red line at our graph. So let it be a red one. And let's choose the corresponding color. So this is the red column. And if we summarize the first, the second term and the third term, so as a result we get our total average cost function on the graph. This is the green line, and for this reason I choose the green line here. So and now we see that these green colors are represented with this green graph, and we see that our function is convex. And it means that it has one solution which brings the global minimum to this function. So it means that we may find such an order quantity, such amount of our order size, which minimizes our total average cost. So as we can see, so minimum value for the total average cost is 29. So if we order something between 4 and 5 liters of orange juice, so let it be orange. Okay, so we will get the minimum value for our total average cost function. So what does it mean? Something between 4 and 5. We consider infinitely divisible product, orange juice, and we may measure 4 liters of orange juice, or also 4.1 liters of orange juice, 4.2 liters of orange juice, so and so on. So it means that we may consider any fraction of liter also. So and it means that if we consider something between 4 and 5, maybe we will further reduce the total average cost function. So let's continue and let's try to understand how to calculate such an optimal order quantity. As we can see, the total average cost function is convex function, and maybe you remember from the topic of nonlinear programming. So if the function, if the objective function is convex, then necessary condition for optimality are also sufficient condition. So it means that if we implement necessary condition right now for our objective function, for our problem of inventory management, so necessary conditions will be also sufficient one. So let's formulate necessary conditions for economic order quantity model. So let's consider our objective function, and let's consider necessary condition for this function. We see that on the second term, variable x is of the -1 power. So, and for this reason, this problem is nonlinear one. Let's consider the first order condition. We should consider the first derivative of x and equate this to 0. And for this reason, let's consider the first derivative of the function z, and if we consider the first term, so the derivative by x is 0, plus, if we consider the second term, so it is f times d times x of the minus first power. So minus first we use here as a parameter times f times d over x minus second power plus the third term we consider, and the first derivative by x is just h over 2. Now we should equate this to 0, and it will help us to understand what is the order quantity which minimizes the total average cost function. Let's do this, and as a result we get minus fd over x second power plus h over 2 equals 0. So because we consider the first order condition, we should consider equality to 0. And after simplification, so we get fd over x2 equals h over 2, and therefore x second power is 2fd over h, and as a result, optimal order size or economic order quantity is just square root from 2fd over h. So it is economic order quantity. And if we substitute this volume into this function, so we consider t0 star, so optimal order interval. So we will get x over d, but now we consider x star over d, and instead of x star, let's consider this fraction. So optimal order interval is 2fd over h and square root and over d, and as a result we get 2f over hd and square root. So it is the optimal order interval or economic order period. So abbreviation EOP. Also, we may substitute this volume x star, the square root from 2fd over h. We may also substitute this into the function z here, and instead of x we consider x star. So we will get optimal cost. So z of x star, it is cd plus fd over x star plus h x star over 2. And if we substitute square root from 2fd over h into this expression, we will get, after the simplification, z of x star, so is c times d plus square root from 2fdh. So I show you the final result, but you may substitute the economic order quantity, this expression, into this one, and you will see that the result is this one. And to resume, we should once again look at this economic order quantity, and we see that it is the fraction in which nominator is 2, positive number, times f, it is positive number, we pay bonus to our purchase manager, times d, demand rate, so it is once again positive number, over h, holding cost, it is also positive number. So, and we see that economic order quantity is positive number. And if we go back to this restriction, we see that our solution, economic order quantity, is feasible because it meets this restriction. As a result, if we consider the case when lead time is 0, so we get our order immediately. When we make an order, immediately we receive our order. So in this case, the inventory policy is order X star, where X star is economic order quantity, when inventory approaches 0. And here we see the formula for economic order period, EOP, and also we see the formula for optimal total average cost. Now let's consider the case when lead time is non-zero but is less or equal than economic order period. In this case, we consider the following graph. So, assume that our purchase manager controls our inventory at warehouse, and when this inventory, our stock, approaches a certain amount, so we should make a new order to our supplier, and while we are waiting for delivery of our order, so we continue to sell our orange juice from our stock. And so when we make an order at this moment of time, our supplier, so assume that my pen demonstrates the dynamic of our inventory at the warehouse, and pencil shows the delivery from supplier. So here we make an order and two processes now starts. So the first process, our orange juice consumption, and the second process, so a track with orange juice from our supplier starts moving, and a moment before we run out of stock, a truck from our supplier approaches our warehouse and is being unloaded, and here once again we receive our required order. So, and from this point we start to satisfy customers' demand, and once again at certain point, so we make a new order, a new vehicle starts from supplier, and once again here we are supplied, we receive the order, and we continue our operations. So the question is, what is the amount of orange juice we should approach here at warehouse to make a new order? So look, for instance, if delivery lead time is, for instance, 10 days, and assume that demand rate is 7 liters per day, so the question is, how many liters of orange juice do we need for these days of lead time? So the answer is rather clear. So we need 10 times 7, or L times D. So, and we see that reorder point now is the following: D times L. So when our stock approaches D times L, we should make a new order X star. And this is the policy when lead time is non-negative but less or equal than economic order period. And our policy is order X star when inventory approaches D times L, reorder point. And now let's consider the case when lead time exceeds economic order period. So it is possible sometimes we deliver from another country and it takes a lot of time, and economic order period is smaller than lead time. For this case, we need to calculate effective lead time. So by the following formula, so L, it is our lead time which is given, T0 star, it is economic order period, so, and N, it is maximum integer less or equal than fraction L, lead time, over economic order period. So we usually denote this with such brackets, L over T O star. And if we consider an example, for instance, lead time is 15 days, but economic order period is 7 days. So let's consider the maximum integer part of this fraction. So 15 over 7, so it is 2 point something, but integer part is 2. So it means that this formula is lead time minus this 2 times 7. So effective lead time is lead time minus n, which we found by this formula, times economic order period. And in this case, optimal policy could be the following. Let's consider the following example. Once again, we consider the graph, and this is the same graph for inventory dynamics as we discussed before, and assume that here when our stock approaches a certain amount, we make a new order, and from our supplier a ship starts moving, and it approaches our warehouse at this moment of time. The next time when we approach, our stock approaches a certain amount, we make a new order, and here the next ship starts moving and approaches our warehouse at this moment of time, and so on. And from this moment of time, so we make a new order. It seems that starting from the second period, so we have a previous case. So we make an order, we receive an order, so and we continue operations, we make an order, so here we receive an order, and so on. So it is time, it is inventory, and the question is, where do we get inventory at this moment of time? Because we should wait for delivery from this period. So where do we get this inventory? The answer to this question could be the following. For instance, we may buy inventory for this period from our local supplier. Yes, maybe it is not such a cheap price rather than from our international supplier, and but nevertheless, first time for the first period we may pay this higher cost. And also another solution would be the following. So the first period we do not consider operations. So in our business plan we assume that we start our operations only from this moment of time. During this period, without operations, we just make a call to our supplier, but we do not sell anything. And also the next call we make at this moment of time, and we start operations only when we receive the order from the first call. So, and reorder point now is D times L efficient, and inventory policy is the following. We order economic order quantity EOQ when inventory approaches reorder point D times L effective. So, and now it is the reorder point. Let's consider an example. Here we assume that demand rate is 100 lamps per day. We consider a hostel, and we manage the stock of electric lamps. So demand rate is 100 lamps per day, and fixed cost to make an order is $100 per each order, and the holding cost is 0.02 dollars per lamp per day. So every measures are given in days, and if, for instance, if demand rate is given for weeks and holding cost is given for days, we should transform so demand rate to days or we should transform holding costs to weekly scale. But in this case, demand rate is 100 lamps per day and holding cost is $0.02 per lamp per day. And lead time is 12 days. And C small is price for one lamp is $1 per lamp. So, and the question is, what is the inventory management strategy? To answer this question, let's consider a solution. Let's consider economic order quantity. It is 2FD over H and the square root. And after the substitution, so we get 2 times F, it is 100, times D, it is 100, over H, it is 0.02, and square root, and the result is 1000 lamps. It is the order quantity. Also, let's consider what is economic order period. To calculate economic order period, so we should find T0 star by the formula X star over D, and it is 1000 lamps over D over 100, it is 10 days. So as we can see, lead time is 12 days, but economic order period is only 10 days. So then we should consider effective lead time. So L effective is L minus N times T0 star, and L equals 12 days minus N. So my N, it is the integer part from the fraction. Nominator is L, 12 days. Denominator is T0, so it is 10 days. Times T0, and T0 is 10 days. So this result is 1, and 12 minus 1 times 10, it is 2 days. And L efficient times D, reorder point, equals 2 days times 100, it is 200. So it is a reorder point. And total average cost could be found as follows. So of course we consider optimal total average cost by the formula C times D plus square root from 2FDH, and we consider C is $1 times D, it is $100, plus 2 times F, 100, times D, 100, times H, 0.02, and square root. And the result is $120 per day, because once again we consider days for as a time period. So answer is the following: order 1000 lamps when our stock approaches 200 lamps, and corresponding cost is $220 per day. This example is over, and let us continue with the example in Excel. Let's continue with the same example as we discussed before, and let's calculate economic order quantity. It is square root, and for this reason we consider sqrt function, and for this function we consider the fraction 2 times f it is 30, times d is 2, over h, and h is 6, and the result is 4.47, and indeed this value is between 4 and 5, so it is optimal to order every time 4.4714 liters of orange juice. And let's calculate what is the minimum total average cost in this case. So it is C times D plus square root from the expression 2 times F times D times H, and the minimum cost is 28.8. So once again, so it is a little bit smaller rather than 29 we discussed before. And as a result, we implement economic order quantity model also for this example. In real life, of course, if it is impossible to order 4.4 units of our products, so of course we make decisions so to the closer integer, or sometimes we consider the closest maximum integer. As a result, we have implemented economic order quantity model also for this numerical example. To resume, at this class we consider economic order quantity model, so the model which is the implementation of nonlinear programming models for inventory management case. Many thanks for attention. See you.